All right, let's get started on chapter 3. Chapter 3 may be I shouldn't say my favorite because there's a lot of favorites I have, but usually the way it works in my class is the chapter I'm currently teaching is my favorite. And so since we're starting chapter 3, I'm going to go ahead and say it's my favorite. It'll be my favorite till we start chapter 4. But why I love chapter 3 is chapter 3 is going to really get into things that I hope each and every one of you use your whole lifetime. Chapter 3 will teach you how to buy a house wisely, buy a vehicle wisely, how to become a millionaire by the time you're 75 or whatever. So I like chapter 3. It deals a lot with money. And well, to be frank, I kind of like money. So just throw it out there. And I'm guessing most of you do too. You might not admit it like I just did, but I'm guessing many of you do. So with that, let's get started on a quick review before we jump into chapter 3. Example 1, we have this problem, and this is great for those who have not finished chapter 2 test or taken it. Just review us. What does this symbol mean if you see f of g of h, class? What does that mean if you see that symbol? Mathematically, what does that mean? Substitute. That means substitute. And yes, I do have a pre-programmed graph calculator for this, but I'm going to do algebra, and then we'll check our answer with that calculator. So on this one, what I can do is I'm going to stack the equations to substitute properly. That's how I do this. So I'm going to stack in the order of f equation first. So here's f of x. It's 3x plus 2. And I'm going to substitute g's equation into f. G's equation is 2x squared. But I'm not going to do that until I substitute h's equation into g. And h is x minus 5. So what I'm going to do in this problem is substitute. And we substitute from the bottom and work our way up. When you substitute, you always substitute into the value of x. And like athletics, as I've said a lot of times this school year, anytime we substitute, as one value enters in for another, the other leaves the problem. It's like it's leaving the game if you think in terms of athletics. So on this particular problem, I'm going to substitute x minus 5 in for this x. And truthfully, what that will create, not that you have to write down, I'll write down in green, what's bonus, is it's going to create what we would call g of h. G of h, right there, you don't have to write that, but I'm going to, will be 2. And instead of this x right there, it'll be the parentheses x minus 5 substituted in. And then we'd square it. That square did not get replaced, so that's a part of the problem. And that right there is g of h. Now we're supposed to find f of g of h. And I've substituted the h into the g. And so that's what I have there. Now, question for you mathematically. According to PEMDAS, let me say it this way. According to PEMDAS, can I distribute this 2 into this parenthesis without doing anything to this power? So would multiplication come first, or would I have to take care of the exponent here first? You'd have to do the exponent. So I can't distribute in. I'm going to leave it like this. I'm just going to leave it in that form, and I will substitute this. So now, what am I substituting? I'm going to use a different bracket. I am substituting this whole g of h. All that portion right there. And where will it go? In for this x and f of x's equation. And that will solve for me what we're intended to find, the f o g o h. All right, so let's just work our way through this. I'd have in blue here this 3. But instead of this x, it gets substituted. I'm going to go ahead and use this bracket because there's 2 parentheses in there. The bracket is just a different type of parentheses. So I'm going to do that just so we can keep track of what's what. And then the plus 2 on the outside. So that right there is my answer in non-simplified form. Let's go ahead and simplify it. Can I multiply this 3 times the 2? Would that affect that square, or am I allowed to do that? Yeah, I could do that. What's 3 times 2? 6. So I would have 3 times 2 is 6. And I can drop this bracket now. So I multiplied those two, 3 times 2. That's what I just did there. And I got a 6. So I'm going to drop this bracket, which leaves me with just x minus 5 squared plus 2. Now that's what we call vertex form. I'm going to leave my answer in vertex form right there. You could FOIL this out or box method that out to simplify it, but I'm going to leave it there for the sake of time. Let's go over to my Desmos pre-programmed graphs, just the shortcut here. No, I won't do shortcut. I was going to say you can go to my page. I'll go ahead and go to Power School Learning. Since this is a new chapter, we're going to go to chapter 3, and it's lesson 1, as it says in the top left-hand corner, 3.1. So chapter 3, lesson 1, you've taken care of the first thing. You've shown up and you've signed in. And I try to simplify this process. There's just showing up, signing in. I'm just combining it to be one thing. So that's number 1. Number 2, we're doing our in-class work. Let's click here to submit our answers to our packet. And so I'm going to click that. And you might notice that, oh, it's not even on there. Well, that's a shame. What I'm going to do, though, is I'm going to right click, or for you on a Chromebook, use 2 fingers to click on Desmos pre-programmed graphs, ask it to open link in a new tab. And I'm going to use my composition. That's what that's called, composition. If you look down the sides, those symbols you'll see on calculator number 5. Calculator number 5 has those symbols. And let's see what our calculator says, if it loads. All right, we got it. So I'm now going to enter in these equations that we already have our answer here. I'm just checking, I'm just proving to you that this calculator works and how it works. So I have 3x plus 2. My g equation is 2x squared. And my h equation is x minus 5. By default, this is going to find f of g of h, which is exactly what I need. This is another way of writing f of g of h using parentheses. That's another way. We're saying the answer should be this right there. And if you just check the graph, if I go ahead and graph my answer, we had 6 times the parentheses of x minus 5 squared plus 2, like that. What do you notice about this answer? Did we do it correctly? You bet. That overlaps. If you wanted to FOIL that out, you could, but that's our solution there. I'm going to leave it in that form. All right, number 2. It says if j of x is 4x squared minus 1, what is the inverse? I shouldn't have said that. That's what that symbol means right there, inverse. That symbol means inverse. Okay, using algebra, I know that I have a calculator for this. What's the formula, or what do we do algebraically to solve for the inverse? Switch x and y. So first we'd have to establish where is y in the problem. It's j of x. So we're going to switch x and y. So this becomes the y here. So I switch x and y. This is the first step. So for y squared minus 1. And now what's our second step after you switch x and y? Solve for y. And so we'll just go through our process here. I have a minus 1. What's the opposite of minus 1? Plus 1. So I add 1 to both sides. So I have x plus 1 equals 4y squared. Before I square root this, I'm going to ask, how do you get rid of a 4 that's in front of a y? Divide, because that 4 is multiplying. So we divide by 4. We can distribute that distribution, or the division, I'm sorry, distribute the division or leave it like that. I'll just leave it in this form for now. So I now have x plus 1 divided by 4. You could write it x over 4 plus 1 over 4 as separate fractions if you like, equals y squared. And finally, what is the opposite of a square? Square root. Does anybody remember what comes with the square root if it wasn't originally there? A plus and minus. And so once you have the y isolated, you rewrite it as j negative 1. And technically, this symbol would mean inverse function, and this won't be a function. So I really shouldn't leave it in that form, but I will just, it'll be inappropriate. But it would be plus or minus the square root. And if we wanted to simplify this, I could simplify the numerator, or excuse me, the denominator. So I'll put the square root of x plus 1. But then I'm going to divide the entire square root. What is the square root of 4? 2. And I'll put 2 in the denominator without being in the square root. So I simplified that. So truthfully, I would need to restrict the domain. If I were going to leave this in inverse notation, that's saying we use this for a function. So I shouldn't say inverse notation, function notation. If I'm going to use function notation, technically I need to say that's it. Leave it as a function, which this will not be. I'll prove it to you. I'm going to close this graph out, and I'm going to open up my inverse, which is graph number 6. I'm going to open that one up and make that one open a whole lot quicker. I'm going to type in my original equation as 4x squared minus 1. And notice the original is in red, as it says. The inverse is in blue. Is that blue a function? Does that pass the vertical line test? No, it fails the vertical line test, which means this is just an inverse relation. So technically speaking, I shouldn't use this symbol here. That would be if it were a function. I'm just going to go ahead and put it in here, y. And this is j negative 1 of x implies inverse function. But was this a function? We said this is not a function. So since it's just a relation, I'll go ahead and leave it as y equals. That's how it technically should be. So that'd be your answer for number 2, unless you wanted to restrict the domain and just say just the positive square root or the negative square root. So a square root looks like half of a parabola, half of a sideways parabola. So the positive would go up, the negative would go down on this plus or minus. And let's go ahead and check our answer. Here's the positive side. So square root of x plus 1. All that divided by 2. Notice, did that overlap the graph? Did that overlap half the graph? Yes. You bet. The positive would be that positive side of the graph. The negative would be the lower half of the graph. So we did do that correctly. All right. Let's see, number 3. It says find the domain of this function. So I'm going to go to a blank graph. I don't have anything special for domain, I don't think. I don't have anything for domain. So I'm just going to go blank graph here. Let me pause. For domain, what do you assume a function's domain is? All reals, unless you see one of 2 symbols. What are the 2 symbols? Square root or a division. Square root or division. That's what I was looking for. And next class in 3.2, we're going to talk about a third option. But we're not there yet. So this one does have division, so you'd think it's not going to be all reals. If you wanted a cheating way to find this quick, here's all you have to do. I was thinking about this the other day. I don't know why I haven't thought of this in the past, but what I have shown you in the past is if you graph it, you could search the graph looking for undefines, but I thought of a better way of doing this the other day. Here's my thought. If you just graph the denominator, can the denominator not equal? 0. So I'm just going to put the denominator by itself. You see how the denominator crosses the x-axis? It has 2 separate zeros. It has 2 zeros. That would be where this graph is broken. So all I did there is graph the denominator to find out where we'd have zeros in our denominator. Now I'll show you algebraically that these are our answers, 0 and 1.5. Let me show you algebraically how that's our answers. You would say you cannot divide by 0. So 2x squared minus 3x cannot equal 0. And we would need to factor this to solve for our 0. Since I have a power greater than 1, you need to factor. On this one, Jordan, what do you see that's in common? This is an easier way of factoring. What's our GCF in the denominator here? X. They both share an x. So if I GCF'd out the x, that's like dividing out an x, reverse distribution, if you will. I'm left with 2x to the first power minus, and if I divide x here, minus 3. Cannot equal 0. Since I've set this up, as a multiplication or a product of 0 here. I know it's a does not equal. You could follow that rule you learned in algebra 2, the zero product property, and say, okay, the only way to multiply and get 0 is that at least one factor has to equal 0. So just break it up, and since our symbols does not equal, break up each factor and say each factor does not equal 0 and solve from there. So x cannot equal 0. That would be a solution that's already simplified. And then to simplify this one, how do you get rid of, to isolate the x? How do I get rid of a -3? We would add 3 to both sides. And so now I have 2x cannot equal 3. And finally, how do you get rid of the 2 that's connected to the x? We would divide. And so we have that x cannot equal 3/2. That's our second solution. Both those two spots, that's where this graph would break. The way I showed you in the past, is I said you can check out the table and look at there. So we have 0. And then if I did 3/2, 3 divided by 2, you would see that's also undefined. All right. Final question. Describe the discontinuities. I'm just going to use the picture here. What type of break is it at 0 here? How does the blue graph break at 0? Is that removable, infinite, or jump? Why is it infinite? Described by the graph. What do you see on the graph that makes you think it's infinite discontinuity at 0? Why would you say this graph is an infinite discontinuity at x equals 0? The blue graph of f, or of k of x rather, goes to infinity at the zeros. They go to positive and negative infinity. So yes, that's an infinite discontinuity. So you'd say infinite discontinuity, or k of x has an infinite discontinuity at x equals 0. Well, we said there's also a break at 3/2, which is 1.5. What type of break is that? Now that I'm clicking the graph, it's removable because it's just a little hole. So you'd say removable discontinuity at 3/2. Removable discontinuity at x equals 3/2 or 1.5. Well, 3.1, let's get started. So 3.1 is all about this thing called exponential functions. I shouldn't say all about, because we're also going to talk about logarithmic. So exponential and logarithmic are what we're looking at today. Exponential, and we're really, logarithmic starts next class, but exponential is what we're going to focus on today. This is where, if you want to get rich, it's going to be because exponential functions are the way the world works when it comes to money. And most people who are rich understand how exponential functions work, and they use them to their advantage. Many people who are broke, it's simply because they do not understand exponential functions, and unfortunately, the exponential functions work against them. It's a fact of life, at least in 2021, that exponential functions are going to affect your life. It's whether or not you know how to use them, or people abuse you with them. It's the way it was going to work. So I really like this unit because it's so applicable to real world scenarios. So with that, let's get started here. The first thing we're going to do is see some examples here of exponential functions. Exponential functions just means the power is in the x is in the power. So that's what that means. If you see that, you can just say the variable or the x. I'll just go ahead and say the variable in case they use a different letter. The variable is located in the power, or you could say in the exponent. And that's why they call it exponential. So here's some examples where you notice that the power happens to have the variable. Some non-examples just show you that the variable is not the power, except for 1 to the power of x. It needs to have any other, we call that a base. So here's the general form for exponential. I'm going to go ahead and get this to you now. and prepare in preparation for next class. Here's the form is what I'm going to say. You have a base raised to some power, and that's going to equal a number. So for example, 3 squared. 3 would be the base. The power would be 2. So 3 squared would equal what number? 9. So that's how I'm going to describe this. The base is 3, the power is 2, the number is 9. 3 squared equals 9. What we're going to learn about next class is a thing called logarithms. And so a logarithm works in this form. Show of hands, how many people have seen logarithms in previous classes? None. Okay. Logarithm works this way. You're going to have this word log. It's going to have a little lower base down here. So log with a base that's down low. A number that can be oftentimes in a parenthesis equals the power. These are inverses of one another. So remember how inverse means switch x and y? It's a rearranging of the value. So here's the example here. It would be log, my base is 3, my number is 9, would equal the power 2. These are inverses of one another. They are inverses. So the logarithm and an exponential are inverses. And that's just kind of an example of how you might see these values related. Okay, so a logarithm and exponential are inverses of one another, and that's what we're dealing with this unit. With that, let's look at some examples. It says, sketch and analyze the graph of f of x equals 4 to the power of x. Now this is exponential. What would you call that 4 right there? The base, the power, or the number? What would you call 4? That's the base. The base always has the power attached. So that's a base. The reason they call this an exponential function is because the power is the variable. So it says describe its domain. So let's just look at the picture. On this domain, how far left does it look like this graph is going? Negative infinity. It never stops. It goes left forever. Now, how far to the right does it look like the graph is going? Okay, now this one doesn't actually stop. It just continues on. So it'll go to infinity. Are there any breaks along the way? Do you see any breaks? No. So this would be all real. So you could write it that way, or you could say XER. Here it is an interval. There it is this inequality, all reals. Okay, it says not only the domain, let's look at the range now. Now the range, the picture is a little tricky because it didn't show you this, but there's an asymptote here. The asymptote is at y equals 0. So go ahead and add yourself a little dashed line and put y equals 0. The reason they call it y equals 0 is because you cross the y-axis at a height of 0. And the x value is always changing, but the one thing that's consistent is every point on this line has a y height of 0. So there's an asymptote here at 0, meaning this graph will not go below 0, nor will it touch. It just gets friend zoned. They get closer and closer without ever touching. So how low does this graph go? 0. Would you put that with a parenthesis or a bracket? Parentheses. So it goes as low as 0. How high does this graph go? Positive infinity. Positive infinity. And another way of writing this is that y is greater than 0, not equal to, but greater than 0, while and otherwise all real numbers. So all real numbers that are greater than 0. All right. Let's see, domain, range, intercepts, without any transformations, without being shifted or anything like that. Every exponential function will go through the point 0, 1. So it'll have a y-intercept, no x-intercept, y-intercept at 1, but no x-intercept. Does not cross the x-axis. Come on, Jordan. All right, and let's see here. We have the asymptote. I already wrote that down in green, or I showed you we have a horizontal asymptote. So just a lot of review values here. And now let's talk in behavior. This graph is one piece of graph, and every piece of graph in my class, we can find two limits. So there's going to be two limits here because it's one piece of graph, and every piece of graph has two limits. So we're going to have two limits. We're going to have the limit as we go to the left and the limit as we go to the right. So there's the limit as we go left. Here's the limit as we go right. What happens as this graph moves left? As you move left forever, does it go high? Does it rise? Does it fall? Does it get flat? Or does it stop at a point? What happens to this graph as you move left? It flattens out. What's the y value it flattens out on? If you trace it to the y-axis, 0. So it gets flat at 0. What happens as you go right? Does it rise, fall, get flat, or stop? It rises. And what's the symbol for rising? Positive infinity. Hey, keep your phone up, please. And finally, is this graph increasing or decreasing? It's increasing on its domain. Yep. Increasing on the domain, or increasing from negative infinity to positive infinity. Okay, so there was a whole bunch of review there. I'm not going to review all those things on each problem because it would just take a long time, as that one did. But I do want to show you one thing here. This let me show you, because this was increasing, we would call this exponential growth. Okay, so on part B, I'm going to skip over part B, but I will tell you this. That's exponential growth because we're growing. You see this next problem, how it's falling like as across its domain? See how it falls? You would call this exponential decay. Exponential decay. Now, I'm not going to do much else on this problem, but it's decay because it's decreasing on the domain. So I will write that note down here at the bottom in case you wanted to later go back and fill in all the other information. So it's decreasing from negative infinity to positive infinity. For that reason, you would call this exponential decay. So I will leave those two notes. And with that, I'm going to give you your first DOL. I'll let you look at the problem and decide. And if you're wondering why is it exponential decay, it's because the power is negative. If you have a negative power or a base that's less than 1 with a positive power, you will have decay. If your base is greater than 1 and you have a negative power, that means you will have decay. If you have a positive or a base greater than 1 and a positive base, it will be growth. It's that simple. It's all based off this power and the base working together. Here's your DOL number 1. I want you to sketch this, and then with it, you might have some information you can select. So first, come up with your correct graph, DOL number 1. All right, based off your answer from here, you could go through and get the answer to part B by looking at the intercepts, where it was supposed to cross the y-axis, and the two limits, the end behaviors. You should be able to get those answers for part B. All right, so now for the properties, that was really kind of what I was going through. The key things I want you to know is without a transformation, they should have a y-intercept of 1 and an asymptote at y equals 0. That should be true as for any exponential function, whether growth or decay, if there is no transformations. Obviously, with transformations, this graph could get shifted up, down, left to right, and stretch, shrunk, all those things. But without any transformations, that's where it would cross through the y-axis and what it would approach. So now let's talk about this graph and its transformation here. So the first thing I want to look at is, or remind you of, is there's two ways of writing 1/2 to the power of x. The equation 1/2 to the power of x. By the way, what do you call that 1/2? In exponential terms, those three words: base, power, number. That's the base. Sorry, it wasn't very clear there. That's the base. What do you call x? The power. Okay, I want to remind you of a rule, and that rule is this: that if you have a base that like a fraction or something like that, and you wanted to take the reciprocal of it to get rid of the fraction, you could do that. You could change this to a power of 2/1 or just 2. But if you take the reciprocal of your base, how it works with the power is your power goes negative, or if it's already negative, it goes positive. So in this particular case, 1/2 to the power of x is the same thing as 2 to the power of negative x, which you wouldn't need the parenthesis. You could just say that's 2 to the power of negative x. Those two will be equivalent to one another. Obviously, in this form, you've changed your base from 1/2 to 2, and you change your power from x to negative x. But those two graphs would be the same. Having said all that, that'll make this decay. So we know we're going to have an exponential decay. This problem wants to know about the transformation here. I'm going to put decay. Is the transformation that's occurring inside with the x, or is it outside of the x? And it's a little tricky. What do y'all think? This is inside. It's tricky because it's not inside this parenthesis. And normally parentheses would say indicate what's inside, what's out. Hey, Lyric, is this +1 inside this parentheses? No, but guess what? We would say this is inside because it's in the power. It's in the power, and for that reason, this will be a horizontal transformation. How will this transformation occur on the graph? I want to say it's inside with x, so it's horizontal. I'm going to add that note here. So if it's horizontal, does adding or subtracting stretch, shrink, shift, or reflect? When you add a 1, does that stretch, shrink it, shift it, or reflect it? Shifts it. It's a horizontal shift. Does x, do x's lie or tell the truth? Lie. So which way will this go? Left 1. It's a horizontal shift, left 1 unit. Left 1. And so when I look at this graph, you'll see that the solid line has been transformed 1 unit left. So from having a y-intercept at 1.01, it now goes to the point 1, 1. That's been the shift. This would not affect my asymptote. My asymptote would still be at y = 0. My asymptote would still be at y = 0, but my graph has shifted left 1 unit. See that for me there? All right, let's try yearly same thing if you don't mind. Part B. So this time, I'm going to focus on h of x with a negative power. So I'm going to write this over here. H of x is equal to 1/2 to the power of negative x. That 1/2, what do we call that? The base. What do you call this? Power. Okay, let's say you wanted to get rid of the 1/2 on the base. You want to get rid of that fraction. And so you want to take the reciprocal. So you wanted to make your base become a 2. What do you have to do to the power? You would flip the signs. And since it's already negative, what happens to my power? It becomes positive power. So this would be h of x is equivalent to 2 to the power of x. So here's my base. Here's my power. Would this be growth or decay if you have a base greater than 1 with a positive power? Will that be growth or decay? This graph will be exponential growth. Now, as far as transformation goes, let's look at these two. If we're describing the transformation, I have a negative. Is that inside or outside? Is it inside with x or is it outside of the x? It's inside the power where the x is, so this will be considered inside. So if it's inside with x, does that make it horizontal or vertical reflection? Horizontal. This is a horizontal reflection, and if it's a horizontal reflection, which axis would it actually cross over? If you're across the y-axis, very good. Across the y-axis. And so in this problem, you'll see that any point that you could find would reflect the x value. So for example, this point right there was left 2 up 4, left 2 up 4. You could see that the x has been reflected. So now it's positive 2 up 4. And that would work all the way across. for that transformation. All right, I have one more. Tell me this time that -2, is that -2 on the inside with x, or is that the outside? That's outside of the x. It's not in the power. So it's outside. If it's outside, is it vertical or horizontal? Vertical. Okay. Technically, there are two different transformations that take place here. Let's talk about the negative. Let me leave that outside there. That negative, what's the negative going to do? Vertical reflection. And if it's a vertical reflection, across which axis? If you reflect vertically, it's going to reflect across the x-axis. It's tricky. It actually goes across the x. Vertical goes across the x. And then not only that, you have this 2 here. What happens when you multiply by 2? Does it shift? Does it stretch, shrink, or does it reflect? It stretches if it's telling the truth. Does this tell the truth? You bet. It's vertical, so it tells the truth. It's a vertical stretch by factor 2.
Not only vertical across the reflection.
That's right. All y values are going to get multiplied by -2. And so this does not have an original graph. So to help you out, let's put the original graph on there. It would go through the points 0, 1, like always. It would go through the point -1, +2, and it would go through the point -2, +4. So go ahead and put those on. This is the graph f of x. We'll go through these points. And then it would approach that asymptote this way. So there's the graph of f of x. The graph of j of x, you would reflect it across the x-axis, and stretch it by factor 2, which just means all y values get multiplied by -2. So this point would go down to be -8. So if that point originally was left 2 up 4, it's now going to be left 2 down 8. So that's 5, 6, 7, 8. I'm just going to put it right there and say that's the point left 2 down 8. This point, which was left 2, or left 1, I'm sorry, up 2, left 1, up 2, is going to be left 1 down 4, because you just multiply it by -2. Each y value gets multiplied by -2. So it's now left 1 down 4. And that one would become 0, 2, 0, -2. And so that would be now how my graph looks. So all the y values just get multiplied by -2. And that would be your graph j of x. Okay. Both of these would have that asymptote at y equals 0. That would not change because when you multiply 0 by -2, it still stays as 0. So that would not change. That asymptote would not change. But all y values would get multiplied by -2. All right, because it's a truth teller, and that's all that happened. Your turn. I want you to try to transform this graph using that transformation there. DOL number 2. All right, now let's talk about this E. The letter E represents a number. I'll show you in Desmos here. I'm going to clear all this off. E represents a number in mathematics. If you put E in the calculator, it's going to say this 2.71. It's very similar to pi, how pi represents a number that does not change. It's not a variable. It's this never-ending number. E is the same way. It's just an exponential value. That's why they use the letter E for exponential. So that's going to be a value here. And it's like a base of, just think of it as 2.72. If pi you think of as 3.14, E is like 2.72. So on this problem, it says use a graph of f of x equals e to the power of x to describe the transformation that results in g of x equals e to the 3x. So before I actually graph this and show it to you, describe to me this 3 here. Is that a horizontal or vertical transformation? Is that 3 inside with x or outside? It's inside. So this will be a horizontal transformation. When you multiply, normally, without a lie, does multiplying stretch, shrink, shift, or reflect? Stretch. Is inside liars or truth tellers? Liars. So this is a horizontal shrink by factor. Now, the way I've typically taught this is I would say you take the reciprocal. So instead of multiplying by 3, you divide by 3. So 1/3. But Dr. Milana has been saying, and as I've done some research, you see it both ways. You really do. Some just say it's a horizontal shrink by factor of 3, and they just leave it as a 3. So I'm not sure. Just be prepared to see it either way. But I'm just going to say here in the notes, horizontal shrink by factor 1/3. So that just means if the normal graph comes through and it hits the point, this is growth because the base is greater than 1. This is exponential growth. If the normal graph hits the point 0, 1, the second point would hit at that base, which is 2.72. So go up where you think 2.72 is and put a dot. This graph is going to curve up like that. There's the original. There's your original graph, f of x. G of x is horizontally shrunk by 1/3. That means every x value gets multiplied by 1/3. So at the x value of 1, this becomes a 1/3. So you just put this point there. 0 would not change. So this graph, every x value would get multiplied by 1/3. So whatever that point is would come over here. This point would get multiplied by 1/3 over here somewhere. 2 would become 2/3. So it would be kind of like this, just inside it and up. Now you might be going, I don't trust you. Can you show me the actual picture? Yes, I can. So here's f of x equals e to the power of x. And then g of x equals e to the power of 3x. And you can see these pictures here that I wasn't lying to you. That is exactly how the graph looks. And there's a picture. Yes, sir. And so there you go. You can see that's exactly how it looks. It's horizontally been shrunk. All right. And now part B. Let's talk about this. What's going to happen? And did I write exponential growth? I did. This time, what happens if you have a negative power with a positive base? So E is like the number 2.72. If you have a negative power, will it be growth or decay? This graph would be exponential decay. So you can go ahead and put that on there. This is exponential decay because you have a positive base, or not a positive base, I'm sorry, a base greater than 1, base greater than 1 with a negative power. That makes it exponential decay. So if your base is greater than 1, if the power is positive, it's growth. If it's negative, it's decay. If your base is less than 1, then the opposite would be true. So we have 2 transformations this time. This negative, is the negative on the inside or the outside? Are we sure? What do y'all think? Inside or outside? Got 30 people in here. Let's get some more ideas flowing. And negative, is that inside with x or outside the x? Inside. So if it's inside, is it horizontal or vertical? Horizontal. This will be a horizontal and a negative. What does that do? Stretch, shrink, shift, or reflect? A negative does stretch, shrink, shift, or reflect? Reflect. It's a horizontal reflections. Now, reflections are tricky. So which axis does it go across? Across the y-axis. That's right. It's backwards of what we normally think. And finally, this +1, inside, or I said +1, -1, inside or outside? Outside. So does that make it vertical or horizontal? Vertical. Whenever you subtract 1, does it stretch, shrink, shift, or reflect? Shift. It's a vertical shift. It's a vertical tells the truth. Y's tell the truth. So -1 goes up, down, left, or right. Down 1. Vertical shift, down 1. I'll just show you the pictures this time. You could take any point that you know the graph is supposed to have. for example, the original graph goes through the y-axis at a height of 1. This reflects that across the y-axis and then goes down 1 unit. Reflects across the y-axis, which doesn't change that point, but then shifts it down to right there. As you can see, that point does go down 1 unit. So from 0, 1 to now 0, 0. Okay, so that's how that would work. With that, I'm speaking too soon. I got one more transformation. This problem, part C. What happens with that 2? Inside or outside? That's inside with the x? That's outside. So vertical or horizontal? That will be vertical. Whenever you multiply by 2, stretch, shrink, shift, or reflect. Stretches if it's a truth teller. Is that a truth teller?
No, it's not. It is.
I am getting. Is that inside or outside? Outside. So does it tell the truth or lie? Truth. So this is going to be a vertical stretch by factor 2. By factor just means you're multiplying. So all y values would just get multiplied by 2. So on this picture, all y values get multiplied by 2. So if it crosses originally the y axis or the y-intercepts at a height of 1, 0, 1, everything gets doubled. So it's now at 0, 2. Notice that's how it works. Any point we get shifted up, not shifted up, I'm sorry, multiplied by 2. Any y value we get multiplied by 2. This would be growth or decay, looking at the picture. Would you call this growth or decay? I'm hearing both. Y'all decide. Is that growth or decay if it's going up from left to right? Growth. All right. You try deal number 3. Graph this problem and decide what has occurred. Well, number 3. All right, let's talk some money. There are a couple of formulas, and I need to pause here. On your lesson exams, every time you've opened it up this year, you might have noticed that there's a deal called a formula chart. We have not used the formula chart all year. Starting out, we're going to have some formulas that you might want to, if you don't have them memorized or you don't just remember them, you might want to go and look at them. They're on this formula chart. So I'm going to use, again, 2 fingers on a Chromebook to right click. And I'm going to open this in a new tab and just show you that the formulas I'm about to give you for today, moving forward, are on this formula chart. Let me zoom in a little bit. On this formula chart, if I go to, where is it? Page 2, you will see exponential functions, what I'm working on. Exponential functions, you have all the formulas you'll need, although I'll keep it simple, and I just use these 2 right there. These 2 formulas are the ones I use. You'll notice the formulas below them are almost exact match as the ones above. And so I'm just going to teach you everything from just using these 2 formulas. That's what I'm going to look at now. So that's on the formula chart. If you're wondering, where do I get this? I'm going to forget this formula. Well, there they are. Okay, so it says here, if a principal, that's a starting amount. So go over here on this principal P and put starting amount. The principal is your starting amount. And an annual interest rate compounded n times a year, the balance A. The A is the final amount. That's the final amount, is the A. So I could have written it in here. So that's your final. P is your starting. What did R stand for? The rate. The N is the number of times compounded per year. Now you might be like, well, what does that mean? I'm going to use a real world example, and you can discover what most of these are. If you were to buy a house and you had to pay the bank monthly payments. Just gave it away. How often do you pay the bank to pay off the loan? How frequently do you have to pay the bank? Once a month. That would, how many months are there in a year? 12. This number of times compounded per year would be 12. Per year is a very key word, is that N is telling you how many times per year. So you pay the bank 12 times. Okay, you buy a car. How often do you have to make car payments?
Every month.
Every month. Again, what would N be for this example? 12. Most of the things you know go off of this formula with 12 being N. Most of the real world things you'll see, N is 12, unless it's the next formula that's on the right side of the page, which we'll get to. That's like credit cards is the next one. It's all right. Or stock market, if you want to make money in the stock market and credit cards are going to be this formula on the right. Things like buying a house or a car are going to be this formula on the left. Okay, so here's example 4A. It says, Miss Salesman, however you say that name, invested $2,000 into an educational saving account for her daughter when she was an infant. The account had a 5% rate, which, by the way, in terms of history of America, that is very low. The average for America since the founding of the stock market, even when you mix in the Great Depression, times of war, anything, 9/11, the things that have really driven down when people got fearful, COVID, all that, the history of the market, if you took it on average, is between 7 and 9%, depending on, I guess, what segment of American bank companies you're looking at. But that's a very low return. And we're going to see what happens to the money. Okay, so anyways, there's the rate. If Ms. Salazman doesn't make any other deposits or withdrawals, what will the account balance be after 18 years? So they start this when you're born. You're born. Your parents, they decide $2,000. They put it in the stock. What's it going to be valued after 18 years if the interest is compounded quarterly? This is what I don't like about this problem, because this is not realistic. We don't do this quarterly, but let's just say we did. Compounded quarterly. How many quarters are there in a dollar? 4. So how many times per year you think quarterly is? 4. N is 4. That just means there's happening 4 times in the year. So here's what we're going to do. Anytime, by the way, for these two formulas, I know I haven't explained the second formula yet. Anytime you see the word compound, if you see the word compound, you know you're using the formula on the left side of the formula chart. I'm saying that because there's 2 formulas we'll be using. And so we're going to use this formula here. Okay, we established N is 4. What is that 5% going to represent? The rate. But for percent, what you'll have to do is divide it by 100%. So it'll be 5 divided by 100. There. Okay, the 2,000, is that the starting amount or the final amount? That's our P. And now finally, did it give us an amount of time that we do this?
18 years.
That's our T. And so we can plug all these in. I have a calculator for this. When these formulas are plugged in, this is number 9. Compound interest or exponential growth and decay. You can go ahead and click that one. The final amount, we don't know the final amount. It says if you don't know it, leave it as an X. So just put that as an X there. The starting amount is $2,000. The rate, you could do it if you're not sure this, 5 divided by 100. There it is, 5 divided by 100. The time is 18. If you look down here, we have compound interest. So I'm going to open up this folder, that little triangle. If you click it, what is N supposed to be? 4. I'm going to move this, to 4. All right. What does that mean? That means our value, there's 2 formulas here. Let me slide this over. As you can see, the formula here right here will tell us the value is $4,891. So this one did not necessarily increase that fast. That's why I told you the rate is a lot lower than American companies are you would expect to return. And so this value, the answer would be $4,891. So your parents started off with $2,000, they invested it, and it's almost, by the time you go to college, almost worth $5,000. Again, it's a small rate, and the higher the rate, return grows a lot faster. So part B, go ahead. Part B, we changed something. I'm going to change, the problem says compounded monthly. How many months are there in a year? Because you got to think per year here. N equals 12. What I'm going to do this time, though, is also change the rate. Go to your rate, and let's just say the rate is 7%. So I want you to see the rate of 7%. So you can do rate is 7 divided by 100 if you want. Let's see how this value turns out. So on this problem, what I'm going to say is A is going to equal, I'm still going to use the 2000 for the P. Let me first write the whole formula. Sorry. A equals P times 1 plus the rate over N times NT. That's our formula. What I'm using this calculator, but basically what it's going to do is it's going to type in 2000 there, plus 1 plus the rate, which is 7 over 100, divided by 12 months. And then it's going to take the 12 and multiply it times the 18 years. That's what the calculator is going to do. So I come over here. We don't know the final amount, so I'll leave that as next. The P is 2000 still, but this time our rate is 7%. And we're going to compound this how many times per year? 12. So change that to a 12. Now how much is that $2,000 turned into? Now your $2,000 is a little over $7,000. Is that better? No one? Yes. Okay, there's about 3 people. Is $7,000 better than $5,000? Yes, how about that? Yes, it's better. So investing in a better company can make a huge difference here. That's $2,000. Now, that's if you just started with 2,000. I'm going to round, since it's money, to 8 cents. Did I write the answer out this first time? I did. I didn't even tell you that. I rounded to the nearest penny. And what I did not write is what you'd technically be plugging into the calculator here. If you did not use my pre-program, you would use 5 divided by 100 divided by 4 and 4 times 18. That's what I typed. That's basically what the calculator did there. All right, one more time. Let's say you did a little bit better than the average and you got 9%. So change your to 9% now. R equals 9 over 100. So change that, your part C, to 9%. And I want you compounded daily. How many times per year is daily? How many days are there in a year? N equals 365. So here's our formula. And so you take your starting amount, which we're saying is $2,000. My rate is 9 divided by 100. My N we're saying is 365. And what the calculator is going to do is basically type all this formula in here to get the amount. So I'm going to come back over here and change it again. I'm still starting with 2,000. Now my rate is 9%. And how many times am I compounding this per year? How many days are there in a year? 365. I scroll down and the calculator tells me now that my $2,000 turned into 10,000. So I want to make sure you're catching the difference here and investing in good companies versus lousy companies. If you got below average 5%, your value is worth $5,000. Basically, we got 5,000. Then I went to the lower end of average and we had a 7,000 return. Now I did a little bit better than average and you have $10,104 out of your, which one's better? Now, is there much of a difference between 5% and 9%? Yes or no? Is that very much of a difference?
Yeah.
Yeah, between 5% and 9%, your money doubles over 18 years. The money doubles. 5%, 9%. They might seem like to you, well, 5 and 9 are somewhat close. It's a matter of your money doubling. And so this is starting with $2,000. And how many of you had jobs right now? If you looked at your check stub, how many of you have realized if it totals up your taxes and all that, you might have made over $2,000. And if you're thinking, okay, if I would have invested that 18 years from now, if I do terrible, it might be worth 5%. If I do great, it might be worth, did I say 5%? I meant to say 5,000. If it does great, it's worth 10 grand. Do you see how money starts adding up? That's just with a one-time investment. We're gonna get into that. First, you try one. Here's your problem. I want you to try DOL number 4. See what number you come up with. DOL number 4. All right, now on your packets, this next slide here that I just shown you, this next slide is not the next slide in your packets, it's backwards. So earlier I had to just kind of combine this. When I gave you your previous formula, I also gave you this formula underneath it. Here's what I want you to know. What do you think A stands for? That's the final amount. What's P? Starting amount. E is that number. What did we say that number was basically when you round it? Oops, earlier. Do you remember?
2.7.
2.72. Think of it as 2.72. What is R? The rate, and T? Time. This happens when something is compounded continuously, meaning it's happening all the time. So the value of your house, you're paying that monthly. Credit cards, though it's kind of tricky, you pay your credit card monthly. However, your interest is compounding all the time. Credit cards, the value racks up quicker because it's always accumulating interest. It doesn't just wait till the end of the month to recalculate. So here's the deal on my housing payment. If I look today, how much I owe to pay off my whole house, if I just wanted to buy it outright, that value would say the same thing tomorrow. And it would say the same thing the next day, all the way up until the next month on the 15th. On the 15th, it's going to recalibrate a whole thing because that's when the 15th is when it recalibrates all my interest because it's monthly. It does it on once a month, and it happens to be in the 15th is when mine happens to be. Car payments would work the same way. Credit cards, though, every day the interest is accumulating. And as soon as you're late, all that interest they throw on. The same goes true, though, in a positive way if you invest in the stock market. Every day, companies are making money or losing money. And every day, it gets accumulated. Okay? So that's when you use this formula is when something's happening all the time or continuously. So on the formula chart, this is the formula on the right. So if you know how many times it happens per year, you use the formula on the left. If something's happening all the time, continuous, or they might say exponential, that's what E stands for, exponential, you'd use the formula on the right. So let's go back to the same problem. This time, what should we say our rate's going to be? Let's do 9. Again, just to compare it to our answer from part C, I'm going to say the rate is 9%. Let's look at how close or how different the values are between doing this daily and continuously. And there's really not that big a difference between daily and continuously. But here's our formula. A, you'll hear me say A PERT, like this. So what we're going to plug in here is 2,000 times E, which means it's happening all the time. The rate is 9%, so it'd be 9 divided by 100 times the amount of years, which was 18. So I'm going to go back to my calculator. All you need to change is our rate. We're going to leave that. No, T, no. What do I need to change? Oh, all I need to do is look down at my value down below. I didn't change anything other than down here. I'm going to take the second formula answer. I'm not going to take this one that we took last time. Instead, I'm going to take this answer. And so you can kind of look at the two values. There's not much of a difference between compounding daily and compounding continuously because they're already pretty close between daily and continuously. You can see that this is a matter of, let's check it out. I think it's only a matter of $2 difference. Yeah, it's only a $2 increase, $2.02 increase going from daily to all the time. The more often the interest is compounded, the quicker it will add up. So going from, say, monthly or quarterly to monthly to daily to continuously, it should always be increasing. All right, I'm going to let you try number 5. And by the way, the key word here, I did not even circle it. The key word is continuously. You see the word continuously or the word exponential. That's when you use a per. Example 5 DOL. I want you to try these numbers and see what you come up with for example 5. Example 6. Now these last two formulas on the formula chart, I have them on there, but honestly, they're exactly the same as the two before it. If you have something that's happening a number of times per year, which this right here is if it happens once per year, that's what that's showing you here. The n is gone. It's like n is 1. And over here, if something's happening all the time, it would be like the a per formula. There are these two formulas on the formula chart, but honestly, they are exactly the same as the one before it. So here is example 6. It says here a state population is declining at a rate of 2.6% annually. That means the state's having less people. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population of the state in 15 and 30 years. So how many times is this decreasing? When it says annually, it's decreasing annually. How many times per year is annually? 1. So this is like the case is n equals 1. If n is 1, you don't even have to write down the n. You can just skip over the n, or you could just put a value of 1. It doesn't matter. I'll go ahead and take the exact formula. I'm only going to use those two formulas just to keep things simple. But if your n is 1, you can basically just remove it for all practical purposes. So on this particular case, we have 11 million as our population. I'm just going to put it as 11. We'll put on the zeros later. So 11 and then 1. It says I have a plus, but I'm going to take the plus away. It's declining. What does that mean about my rate? Negative. So it's going to be negative 2.6 divided by 100. So instead of a plus, I'm going to say minus 2.6. 2.6 divided by 100. And you could put it over 1, or you could just not put it over anything. And then be 1 times 15 or 30. So 15 first or 30 the second time. And so again, using my same calculator, I come up here, my starting amount is, I'm just going to put 11. My rate is a negative 2.6. The time is 15 years. We're saying n is 1. I scroll down. The first amount would be there. The population would, after 15 years, is here. That's the population after 15 years. And if I did this a second time, all you'd have to do is change the years to 30 to see what's the population after 30 years. And it would be just under 5 million. So this population is, you can see it's quickly decreasing. So this is after 15 years. And this is after 30 years. Population rarely decreases. We are seeing that currently in New York and California. I don't know if y'all noticed that. Those states are, declining. People are bailing, and also abortion has something to do with it too. But it's kind of a heavier topic there. Part B. It says now, the one word that's different is it says continuously. What does continuously mean? How many times per year is continuously? All the time. So you use a different formula. Use a PERT. And so this one, if you want to type it in by hand, you would type in 11 million. The rate is negative 2.6 divided by 100 times 15 or 30 if you were doing it the second time. So type these in, see what we get. So 11 million, negative 2.6 time is 30. Here's the second answer. So you can see that it is a difference here. That's after 30 years. And let's come back up and find 15 years as well. There it is after 15 years. This is after 30. All right, your DOLs. And part B. Example 7. There's a table here and we have to come up with an equation. It says the table shows the population growth of deer in the forest from 2000 to 2010 if the number of deer is increasing exponentially. Okay, I want you to get used to this for chapter 3. You need to look for these words. If it says exponentially or continuously, that means you're using the formula A PERT. It says identify the rate of increase and write an exponential model. I have a calculator for writing models. It is regressionism models, number 7. So I'm going to click this here. And when this opens, I'm just going to type in my data. So I have 2000 and I have 2010. The number of deer are 125 and 264. I need to just delete this row out of there. What I'm going to do is I don't want quadratic here. I want to look at exponential. And it says it's increasing exponentially, which means continuous or exponential. I need to go to that one there, not the one above. This would be a PERT. And so I click this one, and this would give me my example, my answer here. And this is from the year 0, which is a little tricky. Let me take this back and say, let's just say if year 1 was 2000, year 1 was 2000, then 2010 is 10 years later, which would be like year 11. You can kind of see it better. This would be my equation right here. And so let me shrink this so we can get it all. So I wanted 2000 to be year 1. And so basically what I did is I took 2000 and minus to make it equal to 1. I minus 1999. And that's what I did here as well to get 11. That would be my equation. That's how you would do this on example 2 or example 7. So let me make this a little more clear over here. What I'm doing for my table is I'm changing the values to be year 1. And so I'm going 2000 minus 1999 to make that year 1 of 125. And then also do the same thing, 2010 minus 1999 to make that year 11. And that kind of made my table more accurate using 2000 as year 1. And I guess I could have just made it year 0. That might have been easier. Just go 0 and 2010. Let me see if that 150. I'm curious how much of a change that'll make here. If we did that 0, 10, that makes that 125. You know what? That's the way to do this. Let me come back one more time. Sorry to make this so confusing. Hate it when I do this, but we're going to say that we're just going to say year 2000 is year 0. We'll start with from year 0. And so that'll make this thing a lot easier to now navigate through. And that's how I'd recommend you do the next one. When I get to the DOL and 264. So using that information, we come up with this equation right here. This value. I'm just going to copy and paste this over. And now we can get our equation. So the equation here would be A equals 125. That's our starting amount, the starting amount. E, the rate is 0.0 I'm going to round this to the nearest, what, 1,000. I'll go 3 decimal places, so 0.075, because the 7 rounds up. And then the x, we'll just leave it like that. So that's our equation. Now I'm guessing part B is going to need this information. So let me copy that. And on part B, it says, so predict how many years it'll take for the number of deer to reach 500. And so if I remove that using this equation, I want to know when the final number equals 500. I can use nsolve for this, or I could solve it. Now I'll do since you haven't seen this math yet, I'll show you the math. So I'd first get rid of the multiplication. So the opposite of multiplication is division. So I'd first divide by 125. I know 5 goes into both values. 5 goes into 500 100 times. 5 goes in 125 25 times. Oh, and this could reduce one more time. That's 4. 500 divided by 125 must be 4. So 4 equals e to the 0.75x. Now, what you're really going to learn next class is whenever you're solving an exponential or a logarithm for that matter, you'll use the inverse. So 4 is the number by itself. That's my number. E is my base. And this right here is the power. So I'm going to go a little bit ahead here. So to solve this thing, what you'll do is you'll convert it to a logarithm. So as a logarithm, you go log, you follow with the base. So the log base e of the number will equal the power. And I'm missing a 0 there. That needs to be 0.75x. I just realized that's my power, 0.75. I need to have a O right there. And let me go back here. 0.75 like that. There, sneak it in. And so the last step I'll do here is I would divide this by 0.075. Now I have my x isolated, and this will be the exact answer. I type that in the calculator, and then we'll do nsolve. So I'm going to come over to my calculators. I do nsolve. And if I were trying to solve this problem originally, I would have just typed it in. 500 equals 125 e to the power of 0.075 x, and I realize I don't have that. I need to have that 0 right there and another 0 right there. Okay, and then y equals 500. That means they're going to cross at a height of 500 since that number is constant. And so when I graph this, I need to zoom out to a height of 500, and there's my answer. It should be 18.5 basically. Let's see if it's 18.5 years. When I type in what I just got, log base e, we'll also learn that next class. You can just type in log, you can do that, but there is a button on the Desmos calculator. Log base a is the same thing as natural log. You'll learn that next class, but in case you don't know that, let me go here, functions, miscellaneous tab. I'm going to do log with the base, and my base is e, and number's 4 here. And we're going to divide all of that by 0.075, and notice we got the exact same answer right there. So nsolving tells us the answer is 18.5 years, basically 18.5 years. Let me simplify that so you just see what I typed in. So approximately 18.5 years. All right. Now your turn. Here's DOL number 7. First, find your equation. And I would treat this as year 0. Okay, so that's year 0, and it's 5 years later. And then part B, go ahead and figure out when you think the population would surpass 850. You can use nsolve for that. All right, finally, let's take a look at our ACP problems here. I have 2 problems for us. It says a radioactive substance, cesium-137, has a half-life of about 30 years. This means that every 30 years, half the amount of cesium-137 present turns into something else. So half-life is really telling you the rate. The rate here is cut in half. So the rate gets cut in half, if you will. Every 30 years. This means every 30 years, it's starting to do something else. Okay, if the initial amount of CCM was 70, the initial amount, that's their P. So P equals 70. Which exponential function, okay, represents the amount of CCM remaining over time in years? Okay, so half of it gets cut in half, the rate here, every 30 years. That's how long it takes to get cut in half. And so what's tricky about this, oh, here it is, every 30 years, is that doesn't mean do it 30 times per year. That means for it to get cut, for the time to go by where it gets cut in half one time, 30 years has to have passed. So you're looking for something with a 0.5 as a rate. So this one's out. That would be doubling. And it's not this formula. That's not how any of our formulas are set up. So that one's just out. It's not even close. So that one's just out. So between these, what you're looking at is the initial amount needs to be 70, which this one's not. Obviously, the answer is F. But to explain this, that's what we call a good old-fashioned typo. That is not right. It should be the amount of time. No, that's why I'm wrong. The initial amount is 70, not 30. What am I doing? I wonder. I was going to say that's just a typo. No, the initial amount is not 30. The initial amount is 70. So here we go. This is the initial amount. It's getting halved. That's like a 1/2 there. So this is like the P times the base. Where that's happening is the rate's getting cut in half, and it does this one time every 30 years. So if the time was 30 years, if time equaled 30, it would get cut half one time because 30 divided by 30 is 1. So it'd cut it in half one time. If time was 60, what would happen is 60 divided by 30 is 2, and they would cut it in half twice. So it'd go from 70 to 35, and then 35 to like 17.5. So that's what's happening there. That's why G is the correct answer. It's because that is our P there. This becomes like kind of like the rate. It's getting cut in half, and it's every 30 years. That's what that means there. Okay. And now let's look at the second one. The population of a small town is modeled by this equation where n is the number of years. In 2004, the population was 45,000. If the annual rate of increase is 7.5%, which equation determines the number of years it takes to double the population? So we want, if the population, the initial is here, we want the final to be 90,000 because that's 45,000 times 2, or 2p. And so I need to have the initial, and okay, so these two are out because the initial is not 90,000, the initial is 45,000. So it's between these two. And now when it comes down to rate, now my rate is 7.5%. So remember, to get rid of your percent, you need to divide by 100%, which would give us 0.075. So the answer would be C here, not the D. And now last one, Jose is purchasing a new car for $27,500. So that's the price of the car. That right there would be the original price. So I'm gonna call that a P. The value of the car decreases. It's gonna be important. That's a negative rate here. That our car is going to decrease in rate. So negative R, a rate of 11% per year. Okay, so R is gonna be negative. Whoops, let me take that back. R is gonna be negative 11% divided by 100%. So the percents would cancel. And so you could just treat this as negative 0.11. And I'll put a 0 in there so it looks a little cleaner. Negative 0.11. Okay. And approximately how many years will it take for the value of the car to reach 12,000? So that's going to be the final amount, the A. So our value decreases per year. Per year is very key for our formulas. So per year means it's happening one time per year, or said another way, that n is 1. So this is the formula with the 1. So I'm going to go to my formula chart, and out of these formula charts, I'm looking at the formula where n is 1, this one right there. So I'm going to copy that formula down. A equals P, 1 plus the rate over n t. And in this particular problem, if you wanted to type it in without my Desmos pre-programmed calculator, you'd say the original amount is 27,500. The final amount is 12,000. We have a negative rate of 0.11. So I did just minus there over, the n is 1, so you don't actually have to put the n in, you can just ignore that division line of n. And then n is 1 again, you could ignore that. And the years we don't know, so I'm going to treat that, you could leave it as x. I'll put it in the calculator as you can leave it as a t, but I'll put it in the calculator as an x. That's what I'm going to try to solve here. So I'll go to my calculator. The final amount is 12,000. The initial amount is 27,500. The rate was negative 11%. And the time we don't know. So if I look at this graph, I need to select here. Let me go select the correct equation. I want to look at a PERT. And so it should take 7.53 years. 7.54. So let's see here. Why is the answer not on there? What did I do wrong here? 27,500 decreases at 11% per year. Oh, it's not PERT. I'm using this formula. So 7.116 or 7.12. Answer would be A. If you're curious, how would you solve that by hand? Well, you would go through, I'll simplify the inside, but while I'm doing it, I'm gonna do 2 steps at once. Since that is multiplying, I divide by 27,500. 27,500. And I'm not sure exactly how that'll simplify, but I can tell you for a fact that the zeros will be canceled away. So it's 120 over 275. I know 5 will go into both of those. So 5 goes in to 12 twice, the remainder 2. So it'll be 24 over, and 5 goes into this 55 times. And that may simplify, but I can't think of anything right off the top of my head that'll divide into those two. So I'm gonna leave it like that. Equals. Now over here we have 1 minus 0.11 basically, which means I'm going to have the number 0.89. I can take away the parentheses, 0.89 to the power of x. Now that I have the simplified, that's my number. This is my base. This is my power. What you'll learn in lesson 3.2 is you'd convert this to a logarithm. So you'd have log, then the base comes next, 0.89. It's an inverse where you switch the x and the y. The y is the number by itself. The x is obviously the x. So I switch those two, so power number switch. And so it's going to be the number value, 24 divided by 55 equals x. If I type that in, I should get 7.116 log. I got to go over here, log with a base. So go to log, or functions, miscellaneous, log with the little base there of a. Now you can type in 0.89 is my base, 24 divided by 55, 7.16, just like the calculator said the answer was supposed to be. So you can see that that is, I can get that a little higher for the notes. That would be the correct answer there.